Open system interconnect. Open system interconnect. OSI layer. OSI layers. This is proposed or standard. This is a standard. This is a reference model prescribed by ISO, standard organization, no, Institute for Standardization, Organization and Standardization, something. ISO has prescribed a reference model for any device. It can be a server, it can be a printer or a router or a switch. Any device that wants to be a part of network has to be designed referring this particular model. Even you can design your own router. All that we need to do is you need to refer this model when you build your router architecture. You can have your own operating system, make sure it fulfills all this standard. Then your operating system can be on another operating system like Windows or like Linux. You can also have on another operating system of your own name, Salem operating system, something like that. The thing is, you need to follow this particular standard so that our operating system can communicate with the other operating system, which is also developed referring the same model. When two persons refers one common model, these two people's the design will match each other, even though they might have designed with their own ideas. Since the standard is same, both can interact with each other. So a person called Shivanadar assembles computer in India, in Tamil Nadu, called as HCL computers. There is another assembler in US, Dell. He also has got his own computer servers. But these two PCs can interact each other. Whatever HCL PC communicates, Dell PC understands. Whatever Dell communicates, HCL can understand. This is possible because these two vendors have referred one common model, which is called as OSI, open. That's the reason, open system interconnect. So this OSI, that's why reason the name, see, open system interconnect. Any device is ready to communicate, open to communicate. Any system is open for interaction. When we follow this particular reference model and design devices, all systems will be ready to communicate when we follow this particular model. That's why the name open system interconnect, OSI, open system interconnect. Now what does this OSI means for we network people? What does it, in what angle we are going to focus this OSI? We are not actually going to focus on the things what operating system takes care in OSI layer. We focus on what's been needed for a network engineer to understand about OSI. OSI reference model can be seen in various angles. Operating system designers will see in one angle, we network engineers will see in different angle, designers will see in different angles. So There are various dimensions for this, but we are going to focus for overall OSI in a network perspective. As a network engineer, what I supposed to know. So in an easy way, if I need to explain what OSI means, is Open System Interconnect prepares my data and sends it over the media. It can be a fiber channel media, it can be a Ethernet media, or it can be a Wi-Fi. It sends my data out from the device. Not only that, on the receiving side, it takes that signal through Wi-Fi or through Ethernet or through fiber channel. It takes the data in, it takes the signal in and converts it back to the data, the exact data that is sent by the sender. That's the job of OSI. Here we see it prepares my data and sends it as a signal out from my computer. On the receiving side, that signal is received and converted back to the same data. No alteration is done. Exactly the same way that I send, the receiver also receives it. If I will be sending him a PDF, he receives as PDF. If I'll be attaching him a document, he receives as a document. So exactly the same form. Or if I'll be requesting a telnet, the destination understands that I'm requesting a telnet and provides the telnet session. For this, there is a need for a preparation. So, when we send some courier or something, there is need for preparation. We cannot simply send whatever we want to send like that. There is a need for a preparation. Similar way, our data need to be prepared and sent out. Let's assume this one as a computer that sends the data out. There is another computer which is going to receive the data. So two devices we have, and both the devices should be following the same method of sending and receiving packet. That's why we have this OSI. So anything that is sent out from this PC receives it and understands the same way that has been sent. So before sending the traffic out, the preparation is very important. In the application layer, that's the topmost layer. In the application layer, by using some application that can interact with the internet, that can talk to the network, by using that application, we prepare our data, we send our data, we attach our data, or we type the message that we want to convey to the remote person somewhere there using email or so an application that can interact with the network is taken by us, and we put the data there. It can be a file that you attach, it can be the typing that you type to send the message, or it can be a video that you go online, like Facebook Live, or it can be an messenger, WhatsApp Messenger or Facebook Messenger, or it can be this Google Hangout that we are talking now. Those are all what? Those are all the application that interacts with the internet. MS Paint is not the application layer that interacts with the network. So an interacting application, the application that can talk to the network, is what we here call it as an application layer. What about the command prompt? I can interact with the network from here. I can say ping www.facebook or .com. I'm able to reach. I can interact. I can check the connectivity between myself and the Facebook. When I say ping packet internet grouper, that's also a protocol. Grouping is also a protocol here. Packet internet grouper, which uses ICMP to generate an echo request packet. Echo request is sent to Facebook, and Facebook has responded me back. We call it as echo reply. So this is what? This is an application layer example. So I use an application, some sort of application. Depending on what I need, I pick different application. If I'm sending mail, you know where I'll go. I will not be going to the command prompt. But when I do telnet, I may use command prompt, I may use putty. There is an application called, actually it is pronounced as putty, but in India people used to call it as putty. It is actually putty, because putty is somewhat weird name in Kerala. We don't use that putty pronunciation for the tool. We call it as putty here, which is putty, the tool which helps us to do telnet, SSH, remote login. So that tool is an application layer actually. It's an application layer tool. So using the application layer, we generate some traffic, and the traffic is now ready for preparation. What preparation? You need to present it. We need to present it. Means what? If I am telnetting, before sending the traffic out, the traffic should be marked somewhere that this is a telnet session. If I am doing HTTP or www, somewhere there should be some notification that these data need to be considered as www. Means, you know, HTTP. So you need to use an HTML protocol to present it. For HTTP, HTML. So there is a need for a presentation protocol. There is a need for a marking saying how the packet needs to be treated on the receiving side. Kind of encapsulation, meaning saying, you know, I'm sending a PDF, this need to be considered as a PDF on the receiving side. So there should be a marking need to be done there. Only then the receiver will know how the packet, how the data need to be treated. When I send PDF, he receives PDF because I have mentioned that this is PDF. You need to treat the zeros and ones, the bits that is coming, as a PDF. That's what presentation job. That's the name. That's the reason why they have given the name presentation. Presentation layer. After presentation layer comes the time frame, session. Session layer. Now session layer is the place where we stamp the timing when the packet should leave the device. If there is any need for response from the destination, within what time the packet needs to come back. See, when I ping www.gmail.com, I'm getting, you know, response time 15 milliseconds, 14 milliseconds, 10 milliseconds, you know, within that time that the reply has come. This is for the reply. Likewise, when I was pinging, the request also went out at a time frame. Who takes care of this timing related stuffs? It's the session layer. That's the job of session layer program. That's the job of session layer. Now, after you set the timer, after you set the timing, Now the packet has to be transported. For the transportation, you need to decide on what sort of transportation is good for this particular data. If I am transporting camels, I need a special vehicle actually. I cannot use a bus, corporation bus, or I cannot use Ola cabs or Uber cabs or any other transport cab service that human being means normal human uses. You need a special lorry kind of vehicle, a big one with a tall walls, so that I can transport camel. But when I want to send some 50 people from one place to another place, I don't use lorry, the lorry that I use for camels. I use some other transport like bus or cab. Depending on, okay, there is another. Let's say you are inviting someone very special and very busy guy from Dubai to India. You will be arranging him a very good flight like Emirates, Ethiopia Airlines, something like that. But when it is we only going from Dubai to India, we may not be always taking the costly solution. Same source, same destination. So let's go by Air India, the cheaper economic flight. We decide on different transportation depending on who travels. Likewise, different protocol has got different time sensitiveness. The voice and the video that you are seeing and listening now, my voice and the screen that you are seeing, the video, needs a special type of transportation. The file that I attach in my mail and send it to you needs different type of consideration. Not the same consideration given to this voice traffic, to this video traffic, and to the FTP traffic, file transfer protocol traffic. Not the same treatment. FTP is treated in different way than my voice and video. File transmission protocol, FTP, can be slow but needs to be reliable. I'm sending a file and that file can be delivered 10 millisecond late or 50 millisecond late or 1 minute also late, no problem. But my voice cannot be delayed. If my voice gets delayed, then there won't be sync on the receiving side. The receiver will not understand the meaning the same way that I conveyed. So the voice traffics and video traffics are time sensitive traffics. The file transfer protocol, the FTP traffics, are not that time sensitive. The mails that you send, the attachment that you make, the video that you send as a file, attachment file, the movie that you send as an attachment file, these are all not time sensitive. The PDF that you send, they are all not time sensitive. But the streaming video on Facebook, live videos on WhatsApp, this particular session that we are now having, these all are time sensitive. They need to be delivered at once without any delay. Now, if there is a time sensitiveness in the data, UDP is used. User datagram protocol is used. UDP. UDP, User Datagram Protocol. UDP, User Datagram Protocol. User Datagram Protocol is used wherever streaming, video, audio, live chat, live videos, WhatsApp chat. This all uses UDP, User Datagram Protocol. Now, wherever time is not a matter, no problem if it is delivered one minute later, no problem. But all that we need is the guaranteed delivery. Then TCP will be seen there in those services. Transmission Control Protocol, TCP, is used wherever high reliable, secure communication is needed. UDP is used wherever best effort delivery, time sensitiveness is seen. So UDP is best effort delivery, meaning UDP will not send some dummy packets called sync packets, will not send some sync packets and wait for acknowledgement. UDP don't do that. They don't send sync packet, synchronization packet, before sending a packet to the destination, before sending the actual packet to the destination. UDP won't be sending a synchronization packet. Sync packet will not be sending sync packet and waiting for acknowledgement. It simply gushes out, sends out, streams out the data very fast without verifying whether the destination is there to receive or not. So UDP is best effort delivery. That's why we call it as best effort delivery. It assumes that destination is there to receive and it keeps streaming. It keeps gushing out. It keeps sending out the data that it wants to transfer. UDP is best effort delivery. TCP is Transmission Control Protocol. Demands acknowledgement. TCP, it has got control over the transmission, not gushing out, not streaming. Before sending the packet, it does something called three-way handshake. What does that mean? I send a dummy packet, a sync packet to the destination before I send the original packet. I send a dummy packet and then I wait for the acknowledgement from the destination for the dummy packet. For the sync packet, I'm looking for sync acknowledgement. Now the destination also wants to send a dummy packet to me to test my connectivity. So as a second handshake, what I'm receiving is acknowledgement for the sync packet that I sent. Not only that, I'm also getting the first handshake from the destination to me. So that is a second handshake for me because I'm getting an acknowledgement for the sync packet that I sent, but it's a first handshake for the destination. As a response, now I send the actual data and the sync acknowledgement for my destination. So there is a three-way handshake involved in this to provide the reliability. We call this as connection-oriented approach. TCP does three-way handshake to establish connection first, to check the connectivity first. If acknowledgements are fine then only the actual data is sent out. That's why TCP we call it as connection oriented. Whereas UDP, it just sends the traffic out without sending any sync packet. It keeps sending the original real packets that it wants to send, believing, hoping that the destination is there to receive it. That's the reason why we got the term best effort delivery. For UDP we called this best effort delivery. TCP we called as connection oriented. TCP sends sync packets and wait for sync acknowledgement. Once the sync acknowledgement comes, only then it sends the actual packet. The three-way handshake happens there. Now, the layer that where these decisions are made, UDP or TCP may to use for our service, that particular layer we call as transport layer, because this is something related to the transportation. How I am going to transport? Am I going to just send it like that, or am I going to transport it after I establish the connection using sync packet? So this is something related to transportation. So the layer is called as transport layer. The transport layer decides whether to use TCP or UDP for the service that you are trying to use. Not only that, the transport layer is also responsible for segmenting the packets, segmenting the data, not packets. What it does is it segments the large data into small packets. See, because we have small cars, bike, we are safe. Assume one a government says you cannot use car, you cannot use bike. Then you will see only tramways or trains. Too many. Why that is not actually seen? Why government allows to have 4-wheelers and 2-wheelers? It's because these are all small boxes. Because it is small boxes, many can use the road. My car can go and my neighbor car can come back. If my car only is big like train, then the neighbor need to wait for a long time for the train to pass, and then he will take his train, and his neighbor has to wait for long time for this my neighbor's car to pass. The cars are like train size, big size, 32 box train, bogie train. Very large packets cannot be transported so easily in the network. Then all cannot use the service. All cannot use the network. So it needs to be segmented so that it will be easy for transportation. Or big data has to be chopped, segmented, so that small segments can easily go through multiple paths to reach the destination. See, between one source and destination, there are many paths in the real world. Internet is a mesh of topology, mesh of network, mesh of connections. So there may be many paths to reach destination. When you have small segments of one big large data, the segments can easily get into various paths and reach the destination very fast, much earlier, and then those segments can be rearranged as big data. So it's good. Segmenting or segmentation of large data is good, and that segmentation responsibility is also taken care by this transportation or transport layer. because this is something related to transport. Segment is an advantage for transportation. So if you are asked to carry a large wind turbine in one go, very difficult. Wind turbine, the wings are very large. So what we do is we dismantle the wings separate, and we send each wing in a separate lorry as a small segment, small part of wind turbine. We send it in different lorries. On the receiving side, we collect all the components of the wind turbine, we put them together, and we have a wind turbine at our home. So when we have a large data to send, it is good to segment, but it needs to be numbered. Only then we will know which segment comes first and which segment comes next. Only then, when we assemble the segments, we will get the exact meaning that was conveyed by the sender. So segmentation is not just segmentation is happening in transport layer. The segments are also numbered one after the other. They are numbered. Segments are numbered, so that when you reassemble it, you can arrange it properly and assemble it. Our data in the transport layer is called as segments. So this transport layer, we learned here one more thing called port numbers. Port numbers. Transport layer provides source and destination port number, source and destination port numbers, source and destination port numbers for every segment. On the sender side, on the sending side, the source port number will be always a random port number, and that port number will be always above 1024. Any number above 1024, and it will be less than 65535. Port number still 1024 is reserved for various services. So when the segment is sent out, the source port number will not use the reserved port number. Source port number will use the port numbers above 1024 to 65535. Only 255. 65535. That's the maximum port number. Any number between this and this will be assigned as a source port number. But the destination port number, depending on the service, it will be one of the reserved port numbers. Say for example, from this computer A, I'm telnetting to computer B. Telnet's port number is 23, which is reserved port number, TCP 23. So the destination port number will be depending on your service. The source port number will be a random port number. Another example, I am doing HTTP to B. From A, I'm requesting for a HTTP page. I'm requesting for a web page to B. So for HTTP, the port number is 80. The destination port number will be 80. The source port number is random. The destination port number is 80 because I'm requesting for HTTP. So TCP 80 is a reserved port number for HTTP. TCP 23 is a reserved port number for Telnet. TCP 22 is a reserved port number for Secured Shell, SSH. TCP 2021 is for FTP. 443 is for HTTPS. Like this we have various reservations. For various service we have port numbers reserved. The reserved port numbers are up to 1024. Depending on your service that you are requesting, the port number will be any number between 1 to 1024. On the sending side, the source port number is a random port number and the destination port number will be any number between 1 to 1024. So transport layer assigns the source and destination port number. It does segment and it picks UDP or TCP depending on what service that you are looking for. So this transport layer is taking care of transportation. Now up to these 4 top layers, from application to transportation, is taken care by your operating system. You no need to do anything for this 80 to be assigned. You go and type HTTP, automatically port number 80 is picked up. Who takes care of it? Operating system. The operating system that you have in your router or the PC, the computer, or your cell phone. The operating system is designed with all these things inbuilt already by referring this industry standard. So we don't have much work to do in this top 4 layers. Windows guys may have something to do, but we don't have much to do here. But on the firewall, when you work on firewalls, we do play with port numbers. But mostly, this is taken care by the operating system itself, the above 4 layer. As a network engineer, we need to understand more the bottom 3 layers. What are they? Network layer, data link layer, and the physical layer. The physical layer, data link layer, network layer. These 3 layers where we have something to tune, understand. Now about the network layer. For every segment, after getting the port number, after deciding TCP or UDP, for every segment, the network layer provides source and destination IP address. So source IP address will be this computer A's IP address, and destination IP address is going to be computer B's IP address. So when I ping, what happens when I ping gmail.com, the source IP address is my laptop's IP address, and the destination IP address is this 172.217.26.165, which is Gmail server's IP address. So source and destination IP address is assigned to every segment of my data by the layer called network layer. See, I am in one network, Gmail is in another network, 172.217. It's not my network. So because my network and Gmail network needs to be connected, we need someone who understands network. We need someone who puts this network together as source and destination. And that is what taken care by this layer. That's why it is called as network layer or IP layer, network layer, where the source and destination networks are made to communicate. This IP address is of 32-bit size, 32-bit binary number. We'll talk about in much more detail in coming class about IP address, the 32-bit IP address that works in network layer. The protocol IP works in this layer. Internet protocol works in this layer. That's why the address that we use to identify the device, we call it as IP address. The protocol IP, Internet protocol, uses this address. For what? For identifying the destination. Then comes the data link layer. This data link layer responsibility is to provide the source and destination MAC address. MAC address is 48-bit size, 48-bit binary size. MAC address is 48-bit binary number. IP address is 32-bit binary number. Data link layer takes the responsibility of assigning the source MAC address and the next hop's MAC address, which is the destination MAC address. The next device MAC address, which is the destination MAC address. Data link layer. Now, this MAC address is unique. The MAC address on my laptop, you will never see anywhere on the world or in the globe. Nowhere. They are unique. Every NIC card has got a MAC address. Your laptop NIC card has got a MAC address. Your laptop Wi-Fi has got a MAC address. My Wi-Fi has got another MAC address. That's a port where the network can communicate. So they need an identification. The MAC address is a burnt-in address. It is burnt-in address. Why it is called as burnt-in address? It is burnt-in address. It is burnt. Means it cannot be erased. Burnt-in. Embossed. Kalvettai pondrathu. Cannot be changed. It's permanent for your device. But if you change the NIC card, you get new MAC address. For every NIC card, it is burnt in. MAC address is also called as physical address. Why? It identifies the box, the physical box. My computer is identified with my MAC address. That MAC address means my laptop. No other laptop on earth has got the same MAC address. That's why it is physical address. It identifies this physical box. And the IP address is called as logical address. The 32-bit address we called as logical address. The logical address, they are called as logical address. The IP address is logical address. The reason is they keep changing. They're not always the same. Your IP address on your laptop is not the same always. Sometime when you try to access internet using the free Wi-Fi available in a coffee shop, you get an IP address. That IP address and the IP address that you use right now to communicate to me, they're not same always. You're in an airport and you're trying to use that free Wi-Fi that is available in airport. That gives another IP address. There in airport, there is a server called DHCP, Dynamic Host Configuration Protocol Server, that provides you an IP address. And that IP address is not the same address that you are using right now to talk to me. Since the address keeps changing, we call it as logical address. IP address is a logical address. It's not permanent. MAC address is permanent. It's burnt-in address, physical address, hard-coded address. Cannot be changed. So this identity, MAC address identity, is provided to your data by the data link layer. The data with this MAC address identity is called as frames. Our data with the source and destination IP address, we call it as packets. In network layer, I called as layer 3. This is layer 1. This is layer 2. The layer 3 address, what it means? It means the IP address. The layer 3 address, once it is added to your data, when it comes from transport layer, the segment, it gets the identity, the logical identity. Now we no more call it a segment, we call it as what? Packets. Once the IP address is given to your segment, it is packet. And the packet comes down and takes the MAC address identity, the unique identity. Once the unique identity is given to your data, we call it as frames, no more packets. It is frames. Now these frames now need to be converted and sent. Converted to what? Converted to a Wi-Fi signal. Converted to a Ethernet signal, depends. If your laptop is now talking to your router through a Wi-Fi, then the physical layer's responsibility in your laptop is to convert the data to Wi-Fi signal. That's what the physical layer does. I'm talking to you and I'm sharing my screen. My data is now converted from frames to what? To Wi-Fi signal. If I will connect a Ethernet wire between my router and my laptop, then physical layer will convert it into Ethernet IEEE standards. When you have Ethernet, your physical layer knows where the signal is coming. Signal is coming on an Ethernet port. So what it does is, it knows that internet is on Ethernet port. So physical layer only can know this, and physical layer converts your data according to the Ethernet standard. But when I don't have Ethernet, when I have Wi-Fi, it's the same physical layer who can realize that signal is coming, internet is coming on the Wi-Fi. So what it does is, it converts the data into IEEE Wi-Fi standards, A, B and G, A, B, G and N standard. That's the responsibility of physical layer. So our data that you are sending here needs to have some preparation, needs to have some additional thing for the packet to be sent out over the media. It can be a physical media, it can be a Wi-Fi media. Not only that, on the receiving side, these things that got added to your data in the 7 layers helps the receiver to exactly understand the same meaning, the same data that you conveyed, sent. So on the receiving side, what happens? The receiving computer will also have a Wi-Fi or Ethernet. The signal comes in. The physical layer takes that signal and converts it into what? Frames. So data link layer receives the frame and checks the destination MAC address. If the destination MAC address of this coming packet is matching with B's MAC address, then B knows that, okay, it is for me only, because the destination MAC address of the sender has put my MAC address. So what it does is, it understands, and then it looks into the next layer, the network layer, and checks the destination IP address. If the destination IP address matches with this destination PC, then the PC understands that, okay, this is surely for me only. MAC address matches, the IP address matches. Then what it does is it goes to the next layer of the data it received and checks what destination port number. If the destination port number of the sender is 80 in the transport layer, the destination device, the receiving device, understands that sender, Mr. A, wants my web page. See, by seeing the port number, he understands. The receiver understands that A needs B's web page. And then for the web page to be sent, the session layer now rewrites the timing. The presentation layer, using the HTML, takes the application and gives as a response. So what you see here is the sender first encapsulated lot of information to the data. On the receiving side, that was decapsulated one layer after the other. This was checking, decapsulating, and it understood the real meaning of the sender. Depending on the request, it responds back. So this type of preparation is needed between these two devices for successful communication. Say for example, if this destination MAC address, if the destination MAC address is unknown, I don't know the destination MAC address. My PC don't know the destination MAC address, B's MAC address. Computer B MAC address, computer A don't know. What happens is the encapsulation will fail. This packet cannot be a valid packet. That is what OSI layer does. It makes the packet to be valid. It prepares the packet so that it can be valid and accepted in the network. All the 7 layer needs to be complete for a packet to go out of the device. If anyone is missing, as I told you, if MAC address, if the destination MAC address is missing, the packet will not go. If the destination port number is missing, packet will not go. Why? What's the use of me sending the packet without telling the purpose of the packet? So, the 7 layers need to be complete. Only then the packet will be passed. The encapsulation will pass. The receiving side, decapsulation happens. Decapsulation on the receiving side, decapsulation happens on the sending side, encapsulation happens. This encapsulation, decapsulation makes this communication to happen. Is there any question on OSI? TCP is slow, but it is reliable. Why? It sends a sync packet and waits for acknowledgement. Only when there is an acknowledgement, the original packet is sent. So it is a guaranteed delivery. Guaranteed delivery, but takes time. It's slow, but highly reliable. HTTP, Telnet, SSH, FTP, this all needs TCP, reliability. Multicasting, streaming videos, audio, these are all live show, internet messenger, Facebook messenger, WhatsApp messenger, Google chat, all this will use UDP. Based on the service that you request, the destination port number of the sender will be varying. Let me explain you with one example. I have a computer whose IP address is 10.0.0.1 and I have a router whose IP address is 10.0.0.2. Now, when I go to this computer and say telnet, what is telnet? Terminal emulation, meaning I want to see the router in my screen here. I want to configure the router by remotely logging into the router. So I sit here and I say telnet 10.0.0.2 so that this router will be seen here. I can configure right from here itself. I need not to go to the router to configure it. The telnet session source address is my own IP address. Destination address is this IP address. The source MAC address is, let's say the MAC address of this computer is AAA. And destination MAC address is this interface MAC address BBB. Source port number will be a random port number more than 1024 I told you. So let's take it as 30,000. 1. Destination port number will be, because I'm telnetting, is going to be TCP23. Yeah. So you got a source port number, destination port number, source IP address is 10.0.0.1, destination IP address is 10.0.0.2, source MAC address, destination MAC address. Now this packet goes here. Router receives it and checks whether the MAC address, the destination MAC address is its own MAC address. Yes, it is matching. So it uncovers and looks into the destination IP address that is also matching. That is also matching. So what it does is next, it looks into the port number and checks whether port number 23 is open here. If it is open, it is going to provide what? The telnet service. Now how the response packet will be? Response. See, this is a request packet, right? It is a request packet. Let's see how the response packet will look like. Now the source port number will be 23 only because you requested whom? 23. So 23 has to respond here. Respond packet now will not have random port number. If you ask 23 to respond, so that was your destination. If you send destination as 23, when destination is replying you back, that is what source, no, because it is replying. Now to what port number it will reply back? It will reply back to whom? 30.0.0. Sorry, not 30. 30,001 port number. See, 30,001 is the source port number. When you are sending it. When you are receiving it, that will be what? Your destination port number. Likewise, what will be the source IP address? Because he is responding. Destination will be the address of the requester. What will be the source MAC address? PBB, router's MAC address. Destination MAC address is AAA. So what I am coming to say is, when I say source port number is a random port number, it is not on the response side. It is on the request side. On the request side, source port number is going to be a random port number and destination port number is going to be the port number as per the service request that you are making. Because I am doing telnet request, my destination port number is 23. If I would have done a HTTP request, my destination port number would have been 80, not 23. If I would have done HTTP, it would have been what? 80. So depending on the service, the destination port number varies. The receiver, when he responds, it will be opposite. Whatever the destination port number you request, that becomes the source, and your random port number will become the destination. Only then, when this response comes, the PC will know that, oh, I'm getting response on 30,001, which means it's the response for my telnet session, because I was requesting telnet, and you can see the telnet here. So collusion domain and broadcast domain. Collusion. Now collusion domain or collusion control, collusion avoidance, you can say anything of this. Collusion domain means collusion control, controller, or broadcast controller means broadcast domain. If there will be a broadcast in a hub, there will be a broadcast. What is broadcast? Whether it is unicast or broadcast, hub is always going to broadcast only. So let's say A is trying to communicate to D. A is communicating to D. As soon as the traffic hits the port, these are all ports, 5 ports I have drawn, they're all connected to one common logical backbone. So the traffic that hits that logical backbone takes that traffic to every device connected to that backbone, meaning every device gets a copy of it, which means broadcast. What is broadcast? Sending to everyone. Sending to everyone is broadcast. So where the broadcast has been carried out or taken care or controlled, it is this backbone. It is this backbone that is carrying, controlling, or taking care of the data to reach everyone. To reach everyone, this is the backbone. This is that controller that takes care of the broadcast. So hub has got only one broadcast. This is the port responsible to carry traffic to everyone. This is the logical backbone, not port, backbone. Not only that, the collusion. See, you have only one common backbone. There is no other arrangement in hub. So you cannot have too many you cannot have too many devices connected to this. The backbone, the only one road, say there is only one narrow road. Small bridge, you remember, try to recall a bridge in a village where only 2 people can simultaneously cross. If more than 2 people try to get into that same bridge, no one is going to pass through now. Traffic jam. It's a small bridge, narrow bridge, one goes, one comes simultaneously. That's the understanding. But there is one bullet, Enfield bullet, got stuck in the middle of the bridge, the third guy, and 2 lorries are trying to pass opposite. There is no place now for one, because one extra bullet has come there, standing in the middle of the bridge. Even these 2 lorries cannot pass through now. Such a narrow road it is. If the collision need to be avoided, they need to stick on to the bridge rule. That bridge rule is 2 people at a time on the bridge. Anything more than that, collusion only. So it is that bridge rule, that one which controls the collusion there. What is the rule? 2 people at a time. So it is that bridge that controls the collusion there. Bridge means everyone knows, okay, 2 device, 2 lorries at a time, not more than 2. That is the one which controls the collusion there. Same way, this hub has got only one backbone, and it will always broadcast also. If you keep adding more device, more broadcast, then this link backbone cannot tolerate more than certain amount of traffic. So to control that, what they have done is they have limited the number of port of hub to 8. 8 is the maximum number of port. We saw that, and that's the maximum amount of data this one common backbone can tolerate. More than 8, if all 8 are communicating at the same time, it can tolerate. If 9th guy comes and tries to communicate, then it's beyond the toleration level. 8 max, that is what controlling. 8 max can be accommodated on this bridge. 9th guy cannot. So it is this one common backbone which is also controlling the collusion. Only one collusion domain and one broadcast domain. Maybe if I have multiple bridge, I may have more number of ports, but I don't have multiple bridge, only one. In a hub you have only one backbone, which is responsible for taking the traffic to everyone, which is also responsible to avoid collusion. It is that one bridge you need to go between these two villages, and it is that one bridge which also has got the rule that 2 lorry at a time to prevent collusion. So collusion controller and broadcast controller is 1 and 1 in hub. Whereas in switch, we know that switch, if the destination is unknown, it will do broadcast. So to reach everyone, to do broadcast, it uses this common logical backbone. Switches uses this common logical backbone to reach everyone. To discover the MAC address, to learn the MAC address of the interface, it needs to do broadcast. Fine. But after they learn the MAC address, what they do is, they don't use this common backbone. See, first time I'm going to a location, I use the main road, which everyone is using, where there is heavy traffic. But once everyone knows the area very well, not everyone is going to use that main road. Only those who are new, those who don't know the destination, will go through the main road. Once the MAC address of the device is learnt, once the destination is learnt, I know all shortcuts, all Kurkusandha to reach that house. I take that Kurkusandha so that I can avoid collusion here, so that I need not to go to every device doing broadcast. I know how to take my own individual path to various destinations. Because I know the MAC address of every device, who is connected where, I can take a unique path. I can take my own path, avoiding this common backbone. Because every port now can reach to other ports by their own unique path, we avoid collusion. So if you have 48 port, all 48 port, after they learn the MAC address, in order to avoid collusion, they take their own unique path. They take their own unique path, which avoids collusion. So 48 port, how many unique paths it can take? 48 unique paths it can take to the destinations. So 48 port switch will have 48 collusion domain. 48 port switch will have 48 collusion domain, collusion controller, which controls the collusion. by avoiding broadcast, by avoiding this same backbone usage, you are preventing collusion there. You are controlling the collusion by taking what? Separate unique path. How many paths you can take? Every port has got its own unique path to reach other ports, which means you got 48 collusion controller. Every port learns the MAC address, which helps them to take unique path. Collusion controller 48. But in order to reach everyone in the switch, you must use this one single backbone, logical backbone only. So number of broadcast domain is still what? Only one. So a switch has got one broadcast domain, and collusion domain depends on the number of ports. Right. But I also want to introduce you something here, even though it is too early, but because you are in a good understanding level. A switch, if you want to break them into multiple logical switches, it is possible. By default, switch will have only one broadcast domain. But if you create logical switches inside one switch, see this, if I have a 48 port, I am dividing that into 12 ports, 4 logical switches. Yep. So this first port 1 to port 12, I have put into a logical switch. Previously, all 48 port was in one big broadcast domain, one big cluster. Now what I have done is, I have broken down that one large broadcast domain into small broadcast domain. What I mean is, if someone sends a broadcast to port 1, it will go up to port number 12. It won't go to 13 onward. It will not hit 13. 24. 13 to 24 will not get affected by this broadcast. Which means what? There's a separate broadcast domain here. Likewise, the broadcast that is happening in this logical switch will affect from 13 to 24, but not 1 to 12 or 25 to 36 or 37 to 42. Sorry, 48. What I'm saying is, there's a separate broadcast controller for each logical switch. But physically it is only one same 48 port switch. If you want to act like multiple logical switches, what do I mean by that? To have more broadcast domains, you can have, and we call it as virtual LAN, VLAN. This is what VLAN means. Previously, when a broadcast is sent on one port, it goes to all 48 ports. Everyone will get that packet. But here, when a broadcast happens in this VLAN, let's say VLAN number 10, this one, VLAN number 20, this one, VLAN number 30, VLAN number 40. Any broadcast happening in VLAN 10 will not affect other VLAN members. What is the advantage? Advantage is, you are localizing the broadcast. Let's say VLAN 10 is for IT department, VLAN 20 is for sales department, VLAN 30 is for production department, VLAN 40 is for entertainment department, which is very important for me. 4 departments. Now there is no business for the IT guy with sales guys. Then why I unnecessarily go and send the broadcast to sales, production, and entertainment when there is no business? Why unnecessarily I should go and consume their bandwidth here by taking my broadcast there? So what we do is we group all the IT computers in one logical group, and we have separate broadcast domain. Now in this switch we have 4 broadcast domain because you got 4 VLANs. After creating VLANs, virtual LANs. If you don't have VLAN, there is only one LAN. So only one broadcast domain. So what I'm trying to make here is one broadcast domain per switch. One broadcast domain is what default for a separate individual switch, physical switch. When you create VLANs, for each VLAN you will have a separate broadcast domain. For each VLAN there will be a separate broadcast domain. Any question? Right. Next is on the router. On the router, every port will have a separate collusion domain and separate broadcast domain. Every single port on a router will have a separate collusion domain and separate broadcast domain. Why? How? See, router is the one which connects multiple networks. Switch, hub, all these devices are same network, LAN device. Here this is WAN device, so multiple networks. I have network 10 here connected, network 20 connected here, 30 connected here, many PCs, 100 PC in 20, 100 PC in 30 network, 100 PC in 10 network. They are connected to this one common router. If any computer from 10.0.0.1 wants to talk to 30.0.0.1, they have to come to the router. Right. Now, if a packet needs to go to everyone in 10 network, it will not be sent to every port in the router. It will be sent only to this port. This is the port that takes to everyone in 10 network. This is one broadcast domain here for 10 network. To reach everyone in 20 network, this is the port. To reach everyone in 30 network, this is the port. Each port has got a separate controller. For 20 network, this is the controller. 20 network will not come here, or will not go here, will not go to this port. Anything needs to reach if there will be a packet that wants to go to everyone in 20 network, this is the link that it will be used. For 30, this will be the link. Same way, if there will be a broadcast coming from 20 network, this port will stop the broadcast. It won't allow the broadcast to pass through. Why? It says, hey, any 20 is in this direction. Why you're coming? You cannot pass through the router. Because on the router, I don't have any 20. Only here you have 20. On the router, I have 10 on the other side, 40 on 30 on the other side. So 20 is only in this direction. When the broadcast comes, it stops the broadcast. It controls the broadcast, saying, hey, 20 is, that's all. Don't come further. Stop here. No broadcast is allowed to pass through the router. If there will be a broadcast coming from this PC 20.0.0.1, but the destination is 10.0.0.1. What router will do is wait. You are coming as a broadcast, layer 2 broadcast, but you want to go to 10.0.0.1. Let me check the routing table. Routing table says 10 is in this direction. Okay, you go like this. So broadcast is stopped there. Not allowed to pass through. So that avoids collusion also here. Unnecessary collusion. Every port knows what network is connected where. That avoids collusion. So every port has got a collusion domain. Collusion controller. There is no broadcast allowed to pass through the router, which avoids collusion. Every interface knows what network is connected where. So there is no need of causing collusion by sending broadcast there. So every port on a router has got one single collusion domain and one broadcast domain. 3 port router, 3 collusion domain, 3 broadcast domain. By default, a switch has got one collusion domain, one broadcast domain, repeating again. By default, switch has got one broadcast domain, and depending on the number of port, collusion domain. But when you create VLANs, each VLAN will have a separate broadcast domain. 4 VLAN, 4 broadcast domain. On the hub, it is always one broadcast domain and one collusion domain. There is no concept of learning MAC address or creating VLANs in hub. So hub will always have one broadcast domain and one collusion domain. An exercise. I have a switch, 24 port switch, connected to another 24 port switch, and this side another 24 port switch. What is the total number of collusion domain and broadcast domain? Wonderful. Thank you. That's what I want to understand. Perfect. You understood very well. There is only one broadcast domain because when any packet sent here, if it is a broadcast, it's going to go to every 24 port, which will also hit here. And because again it's a broadcast, the broadcast keeps continuing till the end of the last port in this last switch. There is no one in the middle stopping. Hey, you cannot go. No more broadcast. No one is stopping there. So there is one single broadcast domain as a whole, and collusion domain depends on the number of port. 56. All right. 52. Right. Here next is, see, there is another confusing terms in networking called control plane and broadcast data plane. Control plane and data plane. Anything that controls the flow of data is a control plane. Anything that controls the flow of data is a control plane. Based on the control plane, the packets are moved on the ports. So they are data plane. So controlling is like, commanding, hey, you should not go like this, you should only go this way. 20 network, go this way. You cannot go the other way is 10 network. So controlling that routing algorithm, the routing table, these are all what controlling. Go this way. You see, you want to go somewhere, you are using a map, Google map, navigating. To go here, to go to this particular shop, your navigator says go this way, go take right, Go straight 700 meters, take right. What is that? It is a control plane. It is just telling you, go straight 700 meters, take right. It is just telling you, it is not pushing you. It is not carrying you. It's your vehicle that then the one which carries you according to the instruction that you got from the control plane. Control plane is also needed. Your car is also needed to carry you. Data plane is also needed. So in networking devices, you have control plane as well as data plane. The ports that carries data as per the control plane's decision is the data plane. The ports that are used to move your packet as per the decision given by the control plane. Routing table is one example for control plane. MAC address table is another example for control plane. This MAC address is in that port, so you don't go to the other ports. What is it? Controlling. Spanning tree protocol in switches are also control plane. Packets are not allowed on the blocked ports, only on the forwarding ports. Any question on control plane and data plane now? Right. So what we have learned is OSI layer, control plane, data plane, collusion domain and broadcast domain. What we are going to learn is IP addressing in the next class. IP addressing. IP addressing followed by subnetting is what the plan for the next class.